Welcome back to Part 6. Now that we are familiar with the item toolkit environment and have configured our primary top-level gate, we are ready to begin the full construction of our logic model using deductive methods. We will start by looking at the immediate, necessary, and sufficient causes that can trigger this catastrophic state. Before we drop our first subgates, let's clarify the specific naming convention we will follow throughout this model. Because gate naming rules are often highly organization-specific, we are going to enforce a clean, standardized approach to keep our canvas scannable. Every gate name in our tree will remain short, always starting with the letter G followed by a brief identifier. The detailed engineering context will be placed entirely within the gate's description field. Following this convention, let's open up our top gate parameters and switch the name to G explosion. We will leave the description as failure to protect reactor vessel to capture the full scope of the hazard. This clean distinction between a short logic label and a detailed description ensures that our entire engineering team can easily audit the model as it scales. Now, let's apply the construction rules we established in Part 4. We want to identify the immediate, necessary, and sufficient causes for our top event, and systematically repeat this process down through the system layers until our branches terminate into basic, undeveloped, dormant, or transfer events. Looking at our physical system diagram, what is the immediate cause of a vessel explosion? There are two direct, concurrent causes: the mechanical failure of the non-return valve, NRV, and input flow failure where the incoming flow is not stopped. If the upstream input cannot be shut down and the NRV remains stuck closed, the vessel will rupture. Let's add these two failure paths to our model. The NRV failure represents a primary component fault that we do not need to break down any further, so it matches the definition of a basic event from our event table. The input failure, however, is a complex subsystem failure that can be further decomposed into sensor, logic, and isolation valve faults. Therefore, we will model the input failure as a subgate, naming it G input, and setting its description to failure to isolate input flow. So what logical relationship binds these two causes together? Because both the NRV failure and the input isolation failure must occur simultaneously to trigger the explosion, they represent a parallel failure pathway. To model this high-restriction relationship, we will change our top gate type from the default or gate to an AND gate. Now we can move down the next branch of our logic tree to decompose G input. Following our construction rules, we must ask, what are the immediate causes that would lead to a failure to isolate the input flow? Looking back at our physical system, the incoming pressure is delivered through two separate lines, input 1 and input 2. Therefore, the direct cause of an input isolation failure is either a failure in the first line or a failure in the second line. Let's expand the tree by adding two new subgates beneath G input. Adhering to our strict naming convention, we will label these short names G input 1 and G input 2. For their descriptions, we can detail them as failure to isolate input stream 1 and failure to isolate input stream 2, respectively. Now, we need to determine the logical gate type for G input. Recall our system analysis from Part 3. Both input streams must be completely shut down to successfully halt a runaway reaction. This means that if either input 1 fails to close or input 2 fails to close, the overall input isolation safety function has failed, and high pressure will continue to feed the vessel. Because the failure of either independent pathway propagates upward, the logical relationship here is in OR gate. Now, let's drill down into the next logical layer by examining G input 1. We need to determine the immediate, direct reasons why the flow through input stream 1 might fail to stop. Looking at our system configuration, input stream 1 is protected by two distinct inline valves, the manual valve, MV1, and the electronic emergency valve, EV1. Because these two valves are arranged in series along the physical pipe, closing either valve is sufficient to completely block the incoming flow. Therefore, for input stream 1 to continue flowing and fail to isolate, both valves must simultaneously fail to close. If even one valve functions correctly and shuts down, the stream is safely isolated. Because both failure conditions must occur together to propagate the fault upward, the logical relationship here is in AND gate. Following our strict naming convention, we will label these short names GMV1 with the description Manual Valve 1 fails to close and GEV1 with the description Electronic Valve 1 fails to close. Moving to the Manual Valve branch, let's analyze GMV1. We must ask, what are the immediate, direct reasons that Manual Valve 1 would fail to close? Based on our system diagram, there are two direct causes. The first is a mechanical failure where the valve itself physically jams, which we call MV1 stuck open. This is a primary component fault that cannot be broken down further, so it maps directly to a basic event from our event table. The second cause is an operational failure where the human operator fails to respond to the demand to close the valve manually. Because this human error pathway can be further decomposed into diagnostic or execution faults, we will model it as a subgate. Following our naming convention, we will give this subgate the short name GOP failure and assign it the description operator fails to respond and close valve. Now, let's determine the logical relationship for GMV1. If either the physical valve gets mechanically stuck open or the operator fails to initiate the closure, Manual Valve 1 will fail to shut down. Since the failure of either independent path is enough to cause the overall manual valve isolation to fail, the relationship must be an OR gate. Let's continue expanding our human error and signaling branches by moving down into GOP failure. We must ask, what are the immediate, direct causes for the operator to fail to respond? Based on our system design, there are two direct pathways. The first is that the operator is simply not available at their station, which represents a primary operational fault that we cannot break down further. This matches the OP not available basic event in our table. The second pathway is that the operator is present but fails to receive the alarm. Because failing to receive an alarm is a complex subsystem failure involving both hardware and signal paths, we will model it as a subgate named GAlarm with the description operator fails to receive alarm signal. Since either the operator being unavailable or the alarm failing to reach them will result in a total human response failure, the logical relationship here is an OR gate. Now, let's dive into GAlarm to determine why the alarm would fail to alert the operator. There are two direct causes. First, the physical alarm unit itself could suffer a mechanical or electrical fault, which is the alarm unit failure basic event already defined in our table. Second, the alarm unit might be perfectly functional but fails to receive the actual activation signal from the sensors. We will model this signal failure as a subgate called G-signal with the description failure to transmit activation signal to alarm. Because either a faulty alarm unit or a missing transmission signal will cause the operator to receive no warning, the relationship for G-alarm is also an OR gate. Finally, let's dive one layer deeper into G-signal to look at our root data source. The activation signal is generated by two distinct physical sensors in the vessel, the temperature sensor, TS1, and the pressure sensor, PS1. Both of these represent primary component faults with known failure rates, so we can add them directly as basic events under the G-signal gate. To determine the logical type for G-signal, think about how our safeguards are engineered. The alarm is designed to trigger if either abnormal temperature or abnormal pressure is detected. Therefore, for the system to completely fail to send out an activation signal, both sensors must fail simultaneously. If even one sensor detects the runaway reaction and transmits its data, the signal path succeeds. Because both independent sensor faults must occur together to cause a total signal failure, the logical relationship for G-signal is an AND gate. It is a long way down, but we have successfully reached the basic events in this path, meaning we cannot deduct any further. We are now completely done with the GMV1 branch. As you can see, as our analysis progresses, the tree quickly becomes much larger and more complex. To keep our workspace manageable, I want to introduce a very handy feature within the item toolkit called the page flag, which leverages the transfer gate logic we discussed in our theory section. This feature allows you to cleanly move an entire subtree onto a separate page. Let's see how this works in practice. We will double-click our GInput1 gate to open its parameters and check the box labeled page. As soon as you click OK, the software automatically transforms this node into a transfer interface, placing the detailed subtree for input 1 onto a brand new, dedicated page. Now, let's repeat this exact same step for G input 2. By applying the page flag to both major input streams, we instantly clean up our main design canvas. The entire tree at the top level is now clear, concise, and easy to audit, while the granular engineering logic remains safely organized right beneath the surface. We are not done with our analysis just yet. Now that our top-level structure is cleanly organized, we are ready to wrap up this section. In our next part, we will dive back into the model to complete the deductive analysis for our input streams. We will leverage our new page navigation to expand the remaining logic under G input 1 for the electronic valve, EV1, and then build out the parallel logic under G input 2 on its separate page. Thank you for watching, and I'll see you in part 7.